Good morning, everyone, and welcome to today's presentation. I am Associate Professor Yasser Madany, and I'm delighted to have the opportunity to share some insights with you. I'm a senior member of IEEE and a senior member of URSI, and today we will be exploring the fascinating world of systems and digital signal processing, or DSP. Throughout this session, we'll cover key concepts, recent developments, and practical applications in these fields. I look forward to engaging with you and discussing these exciting topics. Let's get started. Let's begin by exploring the concept of introduction. Here, we'll set the stage for understanding what systems are and why they are fundamental in various fields. Moving on, we'll look at the representation of systems, which involves how we visually and mathematically describe different systems to analyze them effectively. Next, we'll discuss the interconnections of systems, emphasizing how systems interact and influence one another in complex networks. After that, we'll cover the classification of systems, helping us categorize different types based on their characteristics and behavior. Then, we'll delve into basic system properties, where we identify key features like stability, controllability, and observability that define how systems operate. Moving forward, we'll examine system modeling in terms of differential equations, which provides a powerful mathematical framework to predict system behavior over time. Finally, we'll go over the outline of this presentation, giving you a roadmap of what to expect as we progress through these topics, all connected by the overarching theme of understanding and analyzing complex systems. A system is essentially a combination and interaction of several components working together to perform a desired task. These components can be physical, like hardware, or they can be algorithm-based, which we typically think of as software. It's important to understand that systems don't operate in isolation. They can be interconnected with other systems, forming larger, more complex systems. When this happens, we refer to the individual systems as subsystems. A key point to remember is that a system is characterized by its inputs, which are also called excitations or causes, and its outputs, which are responses or effects. These inputs and outputs are governed by certain rules or laws of operation that dictate how the system functions. Understanding these fundamental aspects helps us grasp how systems work and how they can be designed and analyzed effectively. Now, let's take a closer look at a block diagram representation of a system. This slide illustrates how we can visually depict the components and their interactions within a system. Block diagrams are fundamental because they help us understand the overall structure without getting lost in the detailed complexities. They highlight the key parts and show how they connect and communicate with each other. This approach is especially useful for simplifying complex systems and making them easier to analyze. By using these diagrams, we can better grasp the flow of information or signals, which is essential when designing or troubleshooting systems. Ultimately, this visual tool supports the overall theme of understanding system behavior in a clear and organized way. Let's take a closer look at the interconnections of systems. As we explore this, it's important to understand that systems don't operate in isolation. They are interconnected in complex ways. These connections allow for the flow of information, resources, and energy, which is essential for the system's overall functionality. When one part changes, it often impacts other parts, creating a ripple effect throughout the entire system. Recognizing these interconnections helps us see the bigger picture and understand how different components influence each other. This concept is fundamental to understanding how systems work holistically, and it underscores the importance of considering all parts when analyzing or designing a system. By appreciating these interconnections, we can better predict outcomes and develop more effective solutions. Let's take a closer look at the interconnections of systems. This is a crucial part of understanding how complex environments operate seamlessly. When we talk about interconnections, we're emphasizing how different systems don't function in isolation. They're linked together, sharing information and resources. These connections enable us to create more efficient, resilient, and adaptable solutions. Think of it like a network where each node or system communicates with others, exchanging data that helps the whole network perform better. For example, in a smart city, transportation, Energy and communication systems are interconnected to optimize traffic flow, reduce energy consumption, and improve overall quality of life. Highlighting these interconnections reminds us that to innovate effectively, we must consider how systems influence and support each other. This interconnected approach aligns perfectly with our overall theme of integrated, sustainable solutions. Understanding these links helps us design smarter, more cohesive systems that can adapt to change and meet future challenges. Let's take a closer look at continuous time systems and how we classify them. When we talk about continuous time systems, we're referring to systems where the input and output signals are defined for every moment in time, as opposed to discrete steps. Classifying these systems helps us understand their behavior and how they respond to different inputs. Typically, we categorize them based on linearity, time invariance, causality, and stability. Linear systems are those where the principles of superposition apply, so the response to a combination of inputs is the sum of the responses to each input individually. Time invariance means the system's characteristics don't change over time, so its behavior is consistent regardless of when an input is applied. Causality is a key concept. Causal systems are those where the output at any time depends only on current and past inputs, not future ones. And stability refers to whether the system's output remains bounded for bounded inputs, which is crucial for real-world applications. Understanding these classifications allows us to analyze and design systems more effectively, ensuring they perform reliably within their intended context. And of course, these concepts tie back into the overall theme of system analysis and control, helping us predict, modify, and optimize system behavior. Let's take a closer look at the discrete time system. When we talk about systems in this context, we're classifying them based on how they process signals over time. Discrete time systems are those where the input signals are defined at specific time intervals, rather than continuously. This is different from continuous time systems, which operate over a continuous range of time. Understanding this classification is crucial because it influences how we analyze and design systems, especially in digital signal processing. For example, digital computers inherently work with discrete signals, so knowing whether a system is discrete time helps determine the appropriate methods for analysis and implementation. So, to sum up, the classification of systems into discrete time and others helps us grasp their fundamental nature and guides us in choosing the right tools for analysis and design. This concept is a key building block in our overall understanding of system behavior, especially as we move towards more complex digital systems. Let's take a closer look at this example to see how these concepts come together in practice. What we're focusing on here is understanding the key points thoroughly, but in a way that feels natural and conversational. It's important to highlight the most critical ideas so they stand out to our audience. As we go through, I want you to think about how these points connect back to the overall theme of our presentation. This helps reinforce the message and keeps everything cohesive. Remember, the goal is to make complex ideas accessible and engaging, so don't just recite the slide. Bring it to life with your tone and emphasis. Now, let's turn our attention to the solution. Here, I want to walk you through the key points that can really make a difference. First, it's about understanding the core challenges we've discussed earlier and developing targeted strategies to address them effectively. We need to focus on innovative approaches that not only solve the immediate issues, but also set the stage for sustainable growth. It's important to highlight that these solutions should be adaptable, so they can evolve with changing circumstances and new insights. Connecting these points to our overall theme, remember that a thoughtful, proactive approach is essential for long-term success. By implementing these strategies, we can create a more resilient and forward-thinking framework that benefits everyone involved. Let's take a closer look at linear and nonlinear systems, focusing on their basic properties. When we talk about systems in this context, we're really interested in how they behave and how we can characterize that behavior. One of the key ideas is that linear systems follow the principle of superposition, meaning the response to a combination of inputs is just the sum of the responses to each input individually. This makes them much easier to analyze and predict. On the other hand, nonlinear systems don't follow this rule, and their behavior can be much more complex and less predictable. Now, understanding these properties is fundamental because it helps us decide how to approach modeling and control strategies for different systems. For linear systems, many analytical tools are available, which simplifies the process. But for nonlinear systems, we often need more advanced methods or approximations. Recognizing whether a system is linear or nonlinear is the first step towards selecting the right analysis technique, ensuring that our study and control efforts are both effective and efficient. This distinction really ties into the overall theme of system analysis. Knowing the nature of the system guides our entire approach. Let's take a closer look at linear and nonlinear systems, focusing on their basic properties. When we talk about system properties, we're really referring to fundamental characteristics that help us understand how these systems behave. These properties are crucial because they influence how we model, analyze, and control different systems in engineering and science. For linear systems, key properties include superposition and scaling. Superposition means that the response caused by two different inputs can be added together to find the total response. Scaling indicates that if you multiply an input by a constant, the output scales by the same constant. These properties make linear systems much easier to analyze and predict. On the other hand, nonlinear systems don't follow these rules. Their responses can be much more complex and unpredictable, which is why they often require different analytical techniques. Recognizing whether a system is linear or nonlinear helps us choose the right approach for analysis and control design. Connecting this to the overall theme, understanding these basic properties lays the foundation for more advanced concepts in system theory. It helps us determine the best methods to analyze, simulate, and control various systems, ensuring we can tackle real-world problems effectively. Now, let's look at another example to really bring this solution to life. This is example 2, and it helps clarify how the approach we've discussed can be applied in a practical setting. When we walk through this, you'll see how the key concepts we've covered come together to produce a clear, effective outcome. Remember, the main idea is to understand how this example illustrates the core principles we've been focusing on, and how it connects to the overall theme of the presentation. So, as we go through it, think about how these insights can be adapted to your own context. This example serves as a concrete illustration of the solution in action. Now, let's look at solution. Example 3. Here, I want to emphasize that this is just one way to approach the issue, and it's important to see how it fits into the bigger picture we've been discussing. What we're highlighting is a practical example that demonstrates how these concepts can be applied in real-world situations. By walking through this example, we can better understand the specific steps involved and how they contribute to solving the problem. Remember, the key takeaway is not just the example itself, but how it illustrates the core ideas we've been exploring throughout this presentation. So, as we go through this, keep in mind how these solutions can be adapted or expanded to meet different needs or challenges. Let's take a closer look at how signals are represented in both the time domain and the discrete domain. For example, yn represents a discrete time signal at a specific time n, while yn_n0 shows us the same signal shifted by n0 samples. Similarly, in continuous time, yt is the signal at a particular moment t, and ytt0 is shifted by t0 seconds. Now, when we talk about xn and xn_n0, we're looking at the same concept, the original discrete signal and its shifted version. In continuous time, it's xt and xtt0. This brings us to the core idea of time-invariant versus time-varying systems. A time-invariant system responds to an input in a way that doesn't change over time. So, if you shift the input, the output shifts in the same way. In contrast, a time-varying system's behavior can change over time, meaning the output might not simply shift when the input shifts. Understanding these properties is fundamental because they affect how we analyze and design systems, especially in signal processing and communication. Recognizing whether a system is time-invariant or time-varying helps us predict its behavior and choose the right tools for analysis. Now, let's take a look at this example to see how the solution can be applied in practice. As you can see here, we're illustrating a specific scenario or case that highlights the key concept we're discussing. The idea is to make the solution tangible and relatable by walking through this example. This helps us understand not just the theory, but how it works in real-world situations. Remember, the goal is to connect this example back to our overall theme, showing how this approach can effectively address the challenges we've identified earlier. So, by examining this example, we can better grasp the practical application of the solution we've proposed. Let's take a look at this example, number 5. Here, we're seeing a practical illustration of the solution we've been discussing. It helps to bring the concept to life and shows how it can be applied in real-world scenarios. By examining this example, we can better understand the key points and see how they connect to the overall theme of the presentation. Remember, the goal is to make these ideas tangible and relatable, so they're easier to grasp and remember. Let's take a closer look at instantaneous and dynamic systems and their basic properties. When we talk about these systems, we're really focusing on how they behave at specific moments in time and how they change over time. The key point here is that instantaneous systems give us a snapshot, like a photograph, of what's happening right now. On the other hand, dynamic systems are all about evolution. They change as time progresses. Understanding these properties is essential because it helps us analyze system behavior, predict future states, and design controls effectively. For example, knowing whether a system is stable or unstable at a given instant can influence how we manage or modify it. These concepts tie into the overall theme of system analysis, where our goal is to understand, predict, and control system responses efficiently. So, grasping these basic properties gives us a solid foundation for working with more complex behaviors in real-world applications. Now, let's take a closer look at causal and non-causal systems, which are fundamental concepts in system theory. Causal systems are those where the output at any given time depends only on current and past inputs. In other words, they don't anticipate future inputs. They react to what has already happened. This property is crucial for real-time processing and control systems, where immediate responses are required. On the other hand, non-causal systems consider future inputs as well, meaning the output can depend on both past and future data points. While this might sound less practical for real-time applications, non-causal systems are often used in offline processing, like signal filtering or analysis, where we have access to the entire data set beforehand. Now, moving on to basic system properties, these are the key characteristics that help us understand and classify different systems. These properties include causality, memory, linearity, time invariance, and stability. Each of these plays a vital role in determining how a system behaves and how we can analyze or design it effectively. Understanding whether a system is causal or non-causal, along with these other properties, allows us to predict its behavior, optimize its performance, and ensure it meets the desired specifications. Remember, these properties are interconnected and form the foundation of system analysis and design. Let's talk about invertible, or sometimes called inverse, systems versus non-invertible, or non-inverse systems. These are fundamental concepts in system theory. When we say a system is invertible, it means that for every output, there's a unique input that produced it. In other words, we can reverse the process, going from output back to input without any ambiguity. This property is crucial when we want to recover original signals or data after processing. On the other hand, non-invertible systems don't have this property. Multiple inputs could lead to the same output, making it impossible to uniquely determine the input just from the output. Now, understanding whether a system is invertible or not ties directly into its basic properties. For example, properties like linearity and time invariance can influence invertibility. If a system is linear and time invariant, we can often analyze its invertibility more straightforwardly using tools like the system's transfer function. Recognizing these properties helps us determine if we can reconstruct inputs from outputs, which is essential in many applications like communications, control systems, and signal processing. So, in the context of overall system analysis, knowing whether a system is invertible guides us on how we can manipulate or recover signals effectively. It shapes our approach to designing systems and algorithms for signal reconstruction, filtering, or even system identification. Understanding these fundamental properties ensures we can make informed decisions about the systems we work with. Let's take a look at this example to understand how the solution works in practice. Here, we see a specific case labeled as Example 6, which helps illustrate the key concepts we've been discussing. By examining this example closely, we can see how the principles we've covered are applied in real-world scenarios. This not only clarifies the solution, but also reinforces how these strategies can be implemented effectively. Remember, the goal is to connect these examples back to the overall theme of the presentation, showing how each piece fits into the bigger picture of solving complex problems efficiently. Let's take a closer look at the Z-plane and the S-plane, which are fundamental tools for understanding system behavior. The Z-plane is used primarily in digital signal processing, while the S-plane is more common in continuous time system analysis. When we talk about stable and unstable systems, we're referring to whether the system's output will settle over time or diverge. In the context of these planes, stability is often visualized by the location of poles. If the poles are inside certain boundaries, like inside the unit circle in the Z-plane or the left half of the S-plane, the system tends to be stable. Speaking of basic system properties, it's essential to understand how these concepts relate to system behavior. Stability, for example, directly influences whether a system's response is predictable and controlled or chaotic and unbounded. Recognizing these properties helps us design better systems, whether digital or analog, and ensures they perform as intended. So, connecting these ideas back to our overall theme, understanding the relation between the Z-plane, S-plane, and system stability is crucial for analyzing and designing reliable control systems. It's the foundation that allows us to predict how systems behave in real-world applications. Now, let's look at the solution with example 7. Here, I want to emphasize that this slide is about illustrating a practical application of the concepts we've discussed. It's one thing to understand the theory, but seeing how it works in a real-world example really brings it home. What's important to note is how the key points we've covered come together in this example to solve the problem effectively. This demonstrates not just the feasibility, but also the efficiency of our approach. By walking through this example, I hope you can see the connection between the overall theme of the presentation and how these solutions can be applied in actual scenarios. It's about turning ideas into action, and this example serves as a concrete illustration of that. Now, let's take a closer look at system modeling in terms of differential equations. Essentially, this approach allows us to describe how a system evolves over time by capturing the relationships between its various components. Instead of just looking at static snapshots, differential equations give us a dynamic perspective, showing us how changes in one part of the system influence others. This method is especially powerful because it provides a mathematical framework that we can analyze and solve, helping us predict future behavior or understand the underlying mechanisms. When we model systems this way, we're connecting the theoretical concepts we've discussed earlier to practical, quantitative tools. In the context of the overall presentation, this approach ties everything together. It's about translating complex real-world systems into manageable mathematical models. This way, we can better analyze, optimize, and control those systems in various applications. Let's now look at how system modeling can be approached using differential equations. Essentially, this method allows us to describe how a system's state evolves over time by formulating equations that relate its variables and their rates of change. The key point here is that differential equations provide a powerful and flexible framework for capturing the dynamics of complex systems, whether in engineering, biology, or other fields. By expressing system behavior through these equations, we can analyze stability, predict future states, and even design control strategies. This approach ties directly into our overall theme of understanding system behavior from fundamental principles. It emphasizes that many real-world systems, be they mechanical, electrical, or biological, can be effectively modeled and studied through their differential equations, giving us deep insights into their operation. Now, let's take a closer look at how we model electrical systems using differential equations. Essentially, when we analyze these systems, we're translating the physical behaviors, like currents and voltages, into mathematical language. This is done through differential equations, which describe how these quantities change over time. By formulating the system in this way, we can predict its response to various inputs and understand its dynamic stability. This approach is fundamental because it connects the physical realities of electrical components to the analytical tools we use for design and analysis. So, understanding this modeling process is key to grasping how we control and optimize electrical systems in real-world applications. And that brings us to the end of our presentation. I'd like to share my contact information in case you have any questions or want to connect further. You can reach me via email at contact@Madany.com or Dr. Yasser, Madany@yahoo.com. Additionally, I'm available through Madany at IEEE.org. Feel free to visit my website at https://imadany.com for more resources and updates. Thank you very much for your time and attention today. I truly appreciate your interest and engagement. If you found this presentation helpful, I encourage you to stay in touch and explore the topics we discussed further. Thanks again, and I look forward to connecting with you all in the future.